we're looking at statistical procedures for drawing inferences regarding a mean or average of a group of data. The example we've been working on, a sample of 5 individuals, was asked about sleep. They had an average of 6 hours and a standard deviation for the sample of 3.39. And we wanted to find a 95% confidence interval for the mean of the entire population. We didn't know that number. We know a confidence interval is of the form best guess plus or minus some number of standard deviations. And in this case, we're analyzing a mean, so the standard deviation will be of the form sigma, the standard deviation for individuals in the entire population, divided by the square root of the sample size. For our problem, sample average was 6, so that's our best guess as to what's going to happen in the population. There were 5 data points in our sample. We don't know what sigma, the standard population standard deviation, is, but based upon our data, we could estimate it as being around 3.39. And because that number is an estimate, because we're dealing with means, the distribution will be a t-distribution, not a normal distribution. Students' t-distribution will use the inverse form because we know the probability and are looking for a cutoff score. 95% confidence means that out in the 2 tails of the distribution, we've got 5%. 5 data points means 4 degrees of freedom, and so our Excel function tells us 2.776. In other words, to get 95% of the possibilities, we need to go out from our best guess 2.776 standard deviations. Now, if it were a normal distribution, it would be 2 standard deviations, but it's not. It's students' t. We need to cover more standard deviations because we're more uncertain about things. We don't know whether that is the real population standard deviation or not. So we hit the calculator buttons, do the arithmetic, 6 plus or minus 4.2. We don't know exactly what the population mean is, but we're pretty sure, we're reasonably sure, we're 95% confident that it's somewhere between 1.8 and 10.2 hours. Now that's a very wide interval, but we've got a pretty small sample size, and our sample had a lot of variability in it. In other words, we're not too sure of what's going on here. There's a wide range of uncertainty. Next question. In theory, 8 hours of sleep a night. In practice, our hunch is that students aren't getting that. So the question is it plausible to believe it's really happening, or does our sample average of 6 give us enough reason to believe that students aren't really getting that proverbial 8 hours of sleep? This is a hypothesis test. We're making a decision. Is this the case or not? And so we begin by stating our hypotheses. The null hypothesis is that nothing special is going on here, and so we'll believe the default 8 hours. Versus an alternative that something is going on, that they're getting less than that 8 hours. In symbol terms, we'll quantify things. Our null hypothesis is that this symbol is the Greek letter mu, lowercase, the population mean, the true average for everybody. Our null hypothesis is that it's 8, our alternative is that it's less than 8. That folk are in fact getting less than 8 hours of sleep. We've got reason to believe up front that if it's not 8, it's less than that. We don't believe up front that people are getting more than the recommended 8 hours. Once that's happened, step 3 is to collect our data, and for our 5 data points, we've already worked out the sample mean and standard deviation. And so step 4, we need to compute a test statistic and p-value. We, of course, draw a picture. Null hypothesis was 8 hours of sleep. We got 6, that was our observation. We're looking for this area, but only the one tail. Our test statistic is observed minus expected over standard deviation. We observe 6 hours, expected 8, that was our null hypothesis. We're analyzing a mean, so the standard deviation is the standard deviation of a mean. Sigma, the spread outness of the individual data, divided by the square root of the sample size. Sample size was 5. We don't know what sigma is, but we're estimating from the data that it's around 3.39. And so our test statistic, this works out to minus 1.319. That number is an estimate. We're dealing with means, so we have a student's t-distribution with 4 degrees of freedom. We want to know what, we've got a cutoff score here. We want to know what probability is associated with it. Given the cutoff score, we'll use the dist function to find a probability. It tells us that our p-value is 0.1288. At this point, we need to make a statistical decision. Let's go back. Our p-value is 0.1288. Even if you have been absolutely and completely lost and confused for this entire module, you should know what to do now. What do we do with a p-value that is 0.1288? Do we reject or not reject the null hypothesis? That's a relatively large p-value. Our statistical decision is we do not reject the null hypothesis. Remember, numbers bigger than 0.05 means these are occurrences that are not all that unusual. By not rejecting, remember, we're not trying to draw a conclusion about hypotheses, we're trying to draw a conclusion about sleep patterns. We need an applied decision here. A not reject means not enough evidence. Admittedly, our experiment was pretty small. That sample mean of 6 hours could very plausibly have happened in a universe where students are getting an average of 8 hours of sleep. There's insufficient reason at this time to believe that in the population, students are in fact getting on average less than 8 hours of sleep. Maybe they are, maybe they aren't. We can't say at this point.